Hello, my name is Florentin SMARANDACHE, professor of mathematics at the University of New Mexico, United States. I present you today an overview of Neutrosophic theories and applications. The Neutrosophic theory started about 1995, and it was influenced by the triads we have in our everyday life, meaning opposites and the neutrals between them. So Neutrosophic set is a generalization of fuzzy set, intuitionistic fuzzy set, picture fuzzy set, ternary fuzzy set, Pythagorean fuzzy set, Q-rang orthopair fuzzy set, spherical fuzzy set, and hyperspherical fuzzy set, and many others. The most general type of Neutrosophic set is refined Neutrosophic set or multiple Neutrosophic set, where we have many components for the truth, indeterminacy, and falsehood. Zadeh has introduced the degree of membership in 1965, and he defined the fuzzy set. Atanasov introduced the degree of non-membership or falsehood in 1986, and he defined the intuitionistic fuzzy set. And I introduced the degree of indeterminacy and Neutrosophy in 1995. The first publications was in 1998, and then I defined the Neutrosophic set on three components: T, I, F, truth, indeterminacy, and falsehood, where in a general definition, T, I, and F can be any subsets of the interval 0, 1. In particular, TIF may be intervals, and that's how the interval valued Neutrosophic set was developed, or single valued, which is the most used, and it's called single value Neutrosophic set. Hesitant sets, and it was called hesitant Neutrosophic set. Further on, going on in the indeterminacy and Neutrosophy, indeterminacy and neutrality, which is the most distinction between Neutrosophic set and any other sets. I made the difference between all kind of Neutrosophic sets. For example, indeterminacy in Neutrosophic sets is everything which is between the opposite A and the anti-A. So we have Neutrosophic triplets, meaning A, which is considered an item, concept, notion, idea, sentence, theory, and anti-A, which is the opposite of A, and in between A and anti-A, we have the neutral or indeterminacy part, neither A nor anti-A, or actually partially A and partially anti-A. So because A and anti-A Neutrosophic triplets that are very well known in the world today, we have such kind of triplets like friend, neutral, enemy, positive, zero, negative, male, transcender, female, win, draw or tie game, and lose, small, medium, tall, or true, partially true and partially false, and then false for true indeterminacy, false for membership, partially membership, partially non-membership, and then non-membership, white, red, black, and so on. So in our everyday life, there are many Neutrosophic triplets that inspired me to write about Neutrosophy, how to connect the opposites, how to find the common ideas to uncommon things, and then how to extend the dialectics, which is the the dynamics of oppositions to neutrosophy, which means the dynamics of oppositions and the neutrals or indeterminate in between them. So the neutrals were ignored, but they are very much used. For example, let's say if two countries go to war, A and anti-A, the neutral countries, some of them interfere in one side or the other side. There are also other neutral countries that still remain neutral. So what I wanted to say that the neutrality has a big importance in our everyday life, and the neutrals may change or deviate to one side or the other side. Sometimes we're not very sure about the neutral, and then we call it indeterminacy, not sure if it's in one side or the other side. We have such kind of indeterminacy also in physics. For example, we have proton, neutron, electron, or we have positive particle, neutral particle, negative particle. We have matter, unmatter, and antimatter. So they very much occur in our everyday life, and that's why I thought it's important to extend the fuzzy and especially intuitionistic fuzzy to Neutrosophic set. Further on, I did a refined indeterminacy and refined Neutrosophic set, logic, probability, and statistics, where we could consider, for example, for instead of A and anti-A, we consider a multiple of A, A1, A2, AN, and then multiple opposites, anti-A1, anti-A2, anti-AN, and then the neutrals between them. So we may have neutral A1, neutral A2, neutral AN, and so on. A simple example of refining determinacy we have, for example, in a spectrum of colors. We have white and black, the opposite colors, but in between them we may have many nuances of colors like yellow, pink, red, blue, violet, and so on. So we have indeterminacy 1, indeterminacy 2, indeterminacy 3, 4, 5, and so on. So we actually have an infinite refinement of colors between white and black, or nuances of colors. So using therefore the truth, indeterminacy, and falsehood, I observe that we have degrees of truth, degrees of indeterminacy, and degrees of falsehood, and the degrees are in between 0 and 1. Same thing for probability. For example, we have Neutrosophic probability, which is an extension of classical probability, and in unclear probability, which is probability based on intervals. So a neutrosophic probability, we have neutrosophic probability NP of an event A is the chance that event A occurs and chance that event A does not occur, or we say chance of anti-A, so the opposite event of A occur, and chance of the neutral A, meaning neither A nor anti-A, or some indeterminate part of A. Indeterminacy in statistics also, because statistics is based on classical statistics is based on determinant data, and the probability also on determinant probability distributions. But we have a lot of indeterminacies in our everyday life. We have indeterminate data. Data has degrees of unclearness, vagueness, data which is partially known, partially unknown, or data which is contradictory, incomplete. So in order to study such events based on incomplete and unclear indeterminate data, we have to use Neutrosophic statistics, which is also generalization of classical statistics. Classical statistics is statistics based on intervals, where some indeterminacy it's fixed using intervals, meaning the element is inside of interval. But not all types of indeterminacy can be approached by intervals. It can be approached, for example, by hesitant sets in order to have less work to do, or by quick probability functions, and so on. So it was necessary to use indeterminacy. Neutrosophic sets, logics, probability, and statistics also work on when the indeterminacy is zero. You just simply replace indeterminacy by zero and use T, I, and F, and do all the work. We may have also infinite indeterminacy and zero indeterminacy. So there are many cases. Now, coming back to the degree of indeterminacy, there are some books published, and they are also in at Cornell University. You can download them. You see them here on these links. And getting further are the neutrosophy coming, etymologically speaking, from neutral, which means just neutral, and logi, which means logic. So is the logic of neutral, the ideas of neutral. Since 1995, the Neutrosophic sets has expanded, and then now it's well known around the world. Now, starting about for Neutrosophy started from paradoxes. So since 1980s, I was attracted by opposite ideas and see how can we deal with them. And I try to use them in literature, developing the paradoxes dictics and paradoxes movement in literature, where an excessive use of contradictions, antitheses, oxymoron, and paradoxes gave birth to a movement called paradoxes, which is developed around the world. And then you see many information about paradoxes in this website. which was spread out in the world, and there are essays in 19 languages published, and some interesting ideas and paradoxes manifestos were developed. There are also 15 international anthologies on paradoxes in art, literature, culture, and using Neutrosophy, we use the paradoxes in science as well. And there are hundreds of researchers from tens of countries that contributed to such anthologies. See here one anthology, for example, and then we have many people from many countries contributing papers in many languages. Then Neutrosophy was considered a branch of philosophy, and it extended the dialectics, and in particular the yin-yang ancient Chinese philosophy. Dialectics developed by Marx and Engels, German philosophers, was actually traced into yin-yang ancient Chinese philosophy that was based on opposites like male, female, earth, sky, positive, negative, and was done about 2,500 years ago with many Chinese philosophers, some of them publishing interesting books. So this was the paper published, and my first book on Neutrosophics was published by a British journal, multiple valued journal, which published also the Neutrosophy here, a new branch of philosophy, and was published by the prestigious Taylor and Francis group in United Kingdom and United States, and the journal was called Multiple Valued Logic, an international journal, and volume 8, number 3 from 2002 was dedicated entirely to Neutrosophy, Neutrosophic set, Neutrosophic logic, and Neutrosophic probability. Also is included in prestigious Cornell University side archives, preprints in United States. Now, I started in 1998 using non-standard Neutrosophic set logic and probability. Because the non-standard analysis was a little difficult to understand, it took maybe about 10, 15 years for the Neutrosophic set and logic to be widely spread, because everybody was embarrassed by the initial definition of Neutrosophic set and logic, where I use the non-standard numbers, the monad, binad, in order to define the logic. Because of non-standard analysis, there was a problem to making researchers understand the definition of Neutrosophic set and logic. So on non-standard analysis, I try to use 1 plus, meaning 1 plus epsilon, to represent the absolute truth which is uh, truth in all possible worlds according to Leibniz, and one, which means truth in one, at least one word, which is relative truth also according to Leibniz. So my idea was to be able to make a distinction between absolute truth and relative truth. Similarly, for absolute falsehood, uh, falsehood in all possible world, and relative falsehood, meaning falsehood in at least one world. And similarly for absolute indeterminacy and relative indeterminacy. This one was overcome when an American student at the Atlanta University did the first thesis of doctorate in Neutrosophics. His name was Haibin Wang. I met him at a conference at the University of Atlanta, and he proposed just to give an elementary definition of the Neutrosophic set and logic using only single-valued numbers. So using single-valued numbers was much easier to understand, and then interval-valued numbers for the Neutrosophic components Ti and F was make people better understand. For example, here, interval-valued number where Ti and F are intervals of the set 0, 1, in the same way as interval valued fuzzy set, interval value intuitionistic fuzzy set, and so on. In Neutrosophic set and logic and probability, because the sum of components may be between 0 and 3, we can have all kind of connections between the three components. They may be totally dependent if T plus I plus F is between 0 and 1, almost similar to the intuitionistic fuzzy set, where by indeterminacy was considered like hesitancy between truth and false. Or we may have partially dependent and partially independent components, or totally independent. So it depends on the sources and on the applications of the components and of the Neutrosophic set and logic. Further on, I observed that in our everyday life, it's possible to get values that are above 1 or below 0, and I call them Neutrosophic overset when at least one of the components may be bigger than 1, either true or falsehood or indeterminacy, or less than 0. The same thing, one of them, Ti and F, may be less than 0. And then I wrote a book and I published some papers. For example, let's see for the case when the components may be greater than 0, greater than 1, and less than 0. And we have some elementary examples. Let's see, we have a given company where a full employer works 40 hours per week. And then let's see what happens. Suppose Helen worked part-time, only 30 hours, and the other 10 hours she was absent. Therefore, her membership will be 30 out of 40, meaning 0.75%. So less than 1, meaning part-time. John worked full-time, so he worked 40 hours out of 40 hours. So the degree of membership is 1. So that's it's supposed for everybody working that time. But let's consider people who work overtime. So George worked 5 hours overtime. So George worked 45 hours instead of 40. So we cannot attribute to him the same membership degree as we did to John. John has the membership degree 1, working 40 hours. Since George worked 45 hours, so he deserves a more membership, bigger than 1. So 45 over 40 is 1.125 membership degree. So this is normal in our everyday life. Now, let's see, we had another employee for the same company that worked no hour, so was absent the whole time. His membership degree for that week is 0. 0 over 40, it's 0 degree membership. But now let's consider another employee, Richard, who didn't work that time. Uh, so his membership may be 0. But in addition of not working, he also did damage to the company. For example, he produced damage, like produced some fire in a company or destroyed some machineries there. And then it's considered that, like, let's say, according to negative 20. So we may have his membership degree be negative. It was necessary to consider it negative in order to distinguish Richard's membership from Jane. Jane, not working at all, had a membership degree 0, but she did no damage to the company, so did not deserve any negative thing. But Richard, because he did some damage and didn't work anything, so his membership degree deserved to be less than 0. So examples, clear, easy, elementary examples where people may have degrees bigger than 1 and less than 1. So that's how we design the Neutrosophic overset, meaning when we have at least one component which is above 1 and all the others may be just greater than 0. Under membership, we have some components that are below 0 and the others are up to 1. And off membership means we have all possibilities. I mean, less than 0, between 0 and 1, and greater than 1. So this is called Neutrosophic offset. Some applications and works have been done, so there are many papers here in this work. Then we introduce the Neutrosophic tripolar set, multipolar set, where there are more poles. In the necessity to do a combination of Neutrosophic components, I have developed the N norm and conorm, which were a little different from what was done in a fuzzy set and fuzzy logic, and intuitionistic fuzzy set and intuitionistic logic. We consider, for example, a multiplication of the variables, taking into account, let's see, this one. So we defined we defined the truth part, indeterminacy part, and false part with respect to the previous one. For example, for truth, for union, we consider T1 and T2, while for Neutrosophic union, while for I and F, they go in the same direction, intersection. Now for conjunction, we did the opposite, meaning we have conjunction of truth and union and intersection and union of falsehood and indeterminacy. The most general form of Neutrosophic set was considered n-value refined Neutrosophic set, which is an extension of Lukasiewicz logic. We use true, false, and possible. Clean's logic, we use truth, false, unknown, or undefined. Yang philosophy, but we use we extended Yang in yang and neutral, meaning in between them. And then Klein's logic, truth, false, and unknown, and even further Belknap logic, who has truth, false, unknown, and contradiction. So 4 of them. Now we have defined the n-value logic in a following way. We have for truth, we have split a truth into T1, T2, TP, I into I1, I2, IR, and F into F1, F2, Fs. So all of them are split. And such kind of application is, for example, in a voting system, especially in the United States, where each state votes separately for a candidate, and if the candidate wins, the state gets all the points that the states deserved. So this is the most general form. Now we consider also multiple Neutrosophic set, where we have multiple sources that evaluate the membership or the truth value. So we have like T1, T2, TP with respect to source 1, source 2, source P, and then again indeterminacy with multiple indeterminacies, which may be indeterminacy, unknown, contradiction, vagueness, and so on. So multiple types of indeterminacy and multiple types of falsities, F1, F2, Fs, in order to get a more complex types of from our everyday life. Now, the law of included middle was extended to the law of included multiple middle. So as you know, the law, ancient law of excluded middle was generalized by uh, 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 Fuzzy and even intuitionistic Fuzzy into a law of included middle. And now in Neutrosophic set, we have law of included multiple middle. So because in between the opposites, for example, in between truth and false, we may have multiple types of indeterminacies, like vagueness, uh, confliction, contradictions, and definition, and so on. So this is a book, is mostly a philosophy book about a law of included multiple middle and dynamicity of those middles. Neutrosophic statistics was also based on indeterminacy, and instead of considering interval statistics, we use all kind of indeterminacies. Some indeterminacy cannot be approached only using the interval statistics. So that's why I developed Neutrosophic statistics. I defined in 2014. The first time actually was defined in 1995, but later here was extended into a book. And in Neutrosophic statistics I consider not only the interval, but I consider also applications in using double graphs, for example, using thick functions which are not very clear, which actually can be determined by two curves. So we know the information is between them. Let's see the thick curves. Here, say, like thick curves, we have a curve as in classical, and then it's a thick curve. So the value is somewhere in between. And then was extended to Neutrosophic regression using statistics, using intervals or also hesitance sets. So this is also a thick curve. So we are not able to find the exact result. It's just something in between in a green area because the data is conflicting or is low known. Then pre-calculus, Neutrosophic pre-calculus and calculus were developed further on. So Neutrosophic pre-calculus and calculus, and the defining the derivatives, also using the indeterminacy. The main distinction between indeterminacy between other types of sets and logics and Neutrosophic sets. Neutrosophic crisp set and topology developed together with Professor Salama from Egypt, where it were considered the sets A, B, C, and then all kind of intersections. So Ti and F were replaced by ordinary sets, and then we had all type of intersections between them. Then sub-indeterminacies. So indeterminacy was refined or anyway multiplied, and we got indeterminacy with respect to possibility of dividing or not by 0. Then further on, the Neutrosophic multisets are developed. So a Neutrosophic multiset, it's a Neutrosophic set where one or more elements are repeated with the same Neutrosophic components or with different Neutrosophic components. So this is a generalization of classical multiset and also fuzzy multiset. So in this case, for example, we have the set A, which is a Neutrosophic set, not multiple set, but B is a multiset, Neutrosophic multiset. Why? Because we have two elements that repeat having the same components. Further on, we have, again, some elements that repeat the element A repeats, but having different Neutrosophic components, like an element belonging to a set at a given time, and then at another time belonging to the set with a different set of components here, and here in the same way. Neutrosophic triple structures were introduced by me and Mumtaz Ali in year 2014, and then we extended it in 2016. So the Neutrosophic triplets structures we have a set which has many elements, and such that each element has a neutral element with respect to the given binary operation and an anti-element. And we have the case when the neutral element may coincide with a classical neutral element or not. So sometimes the neutral element may be specific only to an element X. So such kind of elements, if we make such triplets X, the neutral of X with respect to the given law, so this star is the law, and anti-element form a Neutrosophic triplet. For example, X combined to the neutral of X is equal to the neutral of X combined with X is equal to X. So clearly, neutral X is the neutral according to the definition, and anti means X combined with the anti of X is equal to the anti of X combined with X is equal to the neutral of X. Further on, the Neutrosophic duplet structures were also defined. So starting in 2016, and here we have only A and nu of A, and anti-A does not exist. So we have only N and neutral of A. A combined with neutral of A is equal to neutral of A combined with A is equal to A. So these are the Neutrosophic duplex elements. Now, in order to make a total order on a set of Neutrosophic triplets, three functions were defined: the score, accuracy, and certainty functions, and then any three Neutrosophic triplets T1I1 F1 and T2I2 F2 can be compared, and either one is equal to the other, either one is bigger than the other one, or they're equal. So this has been a flag at the beginning, signaled by Riviecio in a paper he published, and then the Neutrosophic community responded and solved this one. Now, an interesting application of the Neutrosophic is in a theory of evolution, because we observe that besides a degree of evolution as developed by Darwin, there is also a degree of involution and degree of indeterminacy, or sometimes degree of neutrality. And let's see some examples. Examples of such applications. So I observed that the animals that were studied when I had a trip to Galapagos and visited the island that Darwin saw, the birds that migrated from the continent to the island, they could fly, but later after a while in the island, they could not fly any longer. So this was interpreted as involution. They did not fly because they didn't need that. They used water in order to get fish, and they developed the legs in order to be able to catch better the fish. Or also an astronaut going to the space for a longer period of time, because of less gravity or even no gravity, his muscle lose from strongness, and when coming back to the Earth, the astronaut has to stay in quarantine in order to recover with the muscles to be able to walk and exercise in the same way. So besides the degree of evolution, meaning adaptation to the new habitation, there are also parts of the body that involved because they're not used or needed any longer. Some remain the same, like neutrality here, because they have the same function in a previous medium as in a second medium, and some are not clear if evolved or not. Further on, in 2013, I introduced the pletogeny, which was a generalization of yin-yang dialectics and neutrosophy, and pletogenic set logic, probability, and statistics as generalization of multivariate logic, and same thing, multivariate probability, multivariate statistics, where many curves take care of, and many sources evaluate an object or an event. So this is the most general one. And the Neutrosophic, the pletogenic set, it's a set which is characterized which has elements such that each element is characterized by many attributes, as in our everyday life. For example, a person is characterized by weight, color, height, education, married status, and so on. And for each of them it's evaluated with a degree. So everybody has a degree of, let's say, education, degree of weight, degree of height, and so on. And the degrees can be measured using fuzzy, intuitionistic fuzzy, Neutrosophic, or other fuzzy extension. So let's see some examples of pletogenic set. A pletogenic logic in the same way. So a proposition, for example, if we consider the logical proposition, it's evaluated by many sources. Similarly for pletogenic set and probability and statistic. Now I'm looking for a pletogenic set. So pletogenic set, it's defined in this way. So it's a set whose elements are characterized by many attribute values, and each attribute value has a degree with respect to the set. So this is the most general. I consider also some applications, some and examples. So this is, for example, a pletogenic fuzzy set, a single value intuitionistic fuzzy set, pletogenic, and so on. How to define the operators, union, intersection, and then complement or negation of the pletogenic sets. So using the pletogenic set, actually we can characterize everything, because every element, every object, human, every being, and so on, even ideas, proposition are characterized by many attributes. And with respect to each attribute, the element has a degree of each attribute. Further on, using combining with a Neutrosophic set and soft set, I define the hyper soft set. So on a hyper soft set, instead of having the function f defined from a set A to the power set of u, we consider the function f defined from a Cartesian product of attributes in to the power set view. For example, if we have a set of houses, we want to know what house is big and of color white, and for example, position peripheral. So we say F of big white peripheral, so all three in the same time is equal to the following houses: house H1, H3, and H7, for example. So these three houses have all types of the previous attributes. Now, very interesting was to use the Neutrosophic dynamic system to prove into a book that it's easier to break a system, Neutrosophic dynamic system. Neutrosophic dynamic system, it's a system that has indeterminacy, and most of systems in our everyday life have indeterminacy, except idealistic systems from science. So it's possible to break. It's a book written together with engineer Andrusha Bătui from Romania. And it's easier to break from inside than from outside a Neutrosophic system. So in order to break something, better to have somebody inside that helps break it than from outside. From outside, it's needed a bigger power to break a system than from inside. So that was the idea. Neutrosophic set and logic were used also in psychology to define the, for example, temperament of a person, because Neutrosophic, we say neuropsychic personality, because for a personality we have a degree of each type of personality. For example, introverted and extroverted. So maybe partially everybody's actually partially introverted and partially extroverted. And the same thing, the threat of a personality may be when we may have threat and anti-threat diagram and varying between both of them. So be actually partially of each of them. Like we know something, we know a little think of everything, like in this way. Sociology. So again, Neutrosophic sociology, where we consider then on each country we have some degree of capitalism and degree of kind of socialism. Why? Because some parts of the system monitored and organized by the state. Others are private. So we have a degree of private companies and a degree of state companies. We have also a degree of democracy and degree of authoritarian system, because some of them have to be imposed by the system. Now, another thing using also Neutrosophy was the spiral Neutrosophic human evolution. So evolution is done in spirals. See, mostly in spirals than linear and directly ascending. So partially ascending and then a little descending and ascending again. The last development was in 2019 about neutrostructures and anti-structures that I developed the neutral algebra and anti-algebra. So what does it mean? A neutral algebra, see, in classical algebraic structures, a space is well determined, the operations is 100% well defined, and the axioms are 100% true. But in our everyday life, things are not like that. We don't live in an equalitarian society where all people are strictly equal. We have inequality between people with respect to richness, with respect to education, and with respect to many things. So in our everyday life, for example, the laws do not apply with the same degree and to all citizens, to all categories of citizens. There are powerful people that are above the law. There are people that are immune to the law. There are people that in a court of law are privileged because they can afford to hire high effective lawyers. Also, there are criminals that escape the jail because they are not caught. There are unfortunately innocent people that go to jail because of sometimes jurisdiction mistakes. There is also hypocrisy and double standard in our everyday life. Some regulation apply to some people, but not to others. Some laws also apply to some categories of people, but not to others. So this one inspired me to define the neutral algebra and anti-algebra, meaning axioms or laws that are not 100% true, meaning that do not apply to all the people, to all the elements, apply only to part of them. You know, it's our life. It's our life. And same thing for operations that apply only partially to some people and partially to others. Or there are even maybe operations or axioms that are totally false in some given societies or some given spaces. So that's why I observed that, for example, if we have a set, we consider a set an ordinary set, and we define an operation on that set. It does not mean automatically that the operation is 100% true. You know, the operation may be 100% true. We call it inner defined, as it done in classical algebraic structures, and then we consider these operations to be Neutrosophic. We write 1, 0, 0, meaning 100% true, 0% indeterminate, and 0% false. But in our everyday life, many laws, many axioms, and many other things are only partially true, partially indeterminate, and partially false. So we call such kind of operations neutral operations. And there are also cases when we have an operation which is totally false. So it will be false degree is 1. So truth degree is 0, indeterminacy degree is 0, and false degree 1. So they're called anti-operations. So we have operations, which are classical operations, learned in schools, in universities. Now, neutral operations, which result from our everyday life, since many laws apply only partially to people, to some people do not apply to other people, or they apply in different degrees to people. Even the taxation law applies differentially to people. Some people are exempted from taxations, others pay little taxes, and while the middle class is taxed to the bone. So as we see, we have different degrees as the laws applying to the elements. So same thing for an axiom. An axiom may be true for all elements, or a law true for all elements, mostly in idealistic or theoretical theory, especially in classical algebraic structures. All axioms are true. They're 100% true. The operations 100% true. In our everyday life, that's not true. I mean, it's only partially true. Axioms that only partially true and that apply only to to a small segment of elements from the space, and or apply to the elements of the space or individual of the space, but in different degrees. So not the same degree to all of them. Same thing from the theorem. We may have a theorem which is false or true in different spaces. You may know that, for example, from the non-Euclidean geometry, where if the axiom, the fifth postulate of Euclid, it's false, then we may have a triangle whose sum of angles is not 180 degrees, maybe bigger than 180 degrees or less than 100 degrees. So in this way, we develop algebra, neutral algebra, and anti-algebra. And in general, we may say structure, neutral structure, anti-structure in any field of knowledge. For example, in physics, in chemistry, in biology, they apply very much. Same thing, the relationships. We may have classical relationship means 100% true, but mostly we have, even with friends, we have partially true, partially false, and so on. As I said before, almost all structures are neutral structures in our everyday life, because we have a lot of indeterminacy, because the operations, relations, and laws are not perfect. They are approximate. We have uncertain data, vague, unclear, conflicted, unknown, or partial data that we know. And then we have also, let's say, example of neutral structures. For example, in a Christian society, the marriage law is defined as the union between a male and female. And this is, let's consider this one degree of truth. But in the last decade, the law has become less than 100% true, since persons of the same sex were allowed to marry. Let's consider this one degree of falsehood. And there are also transcendental people that also can marry. Let's consider this one degree of indeterminacy, because we have a Neutrosophic triplet, male, transcendental or transgender, and female. So we have 3 of them. Another things of laws that work differently. For example, in India, the law of marriage is not the same for all citizens. Hindian religion, men may marry only one wife, while Muslim may marry up to 4 wives. So as you see, the law is different. Same law for in the same country. There also is not possible clearly to distinguish between good and bad, and then that may give a contradiction, or the laws, as I said before, do not apply in the same way for all people. And here there are many papers writing about neutral algebra and anti-algebra from scientists around the world. For example, Professor Ahmed Abdullah, and then Ibrahim and Adelik, and then again Professor Akbar Rezai, Professor Muhammad Amidi, besides the paper written by me. And then we have also Diego Silva Jimenez, Juan Alexis Valenzuela Mayorga, Mara, Esther Roja Ubia, and Noel Batista Hernandez from Latin America, Madeleine Altahan from United Arab Emirates, Bijan Dawaz, Milwayi, and other people. So besides neutral algebra, then applying neutral algebra to neutral geometry, in 2001, I defined the neutral geometry, which is similar to the neutral algebra, a geometric space where at least an axiom is partially true and partially false or partially indeterminate. So this one's particular case, general case is of non-Euclidean geometry, because non-Euclidean geometry is actually referring only to the fifth postulate of Euclid, which is the following: through a point exterior to a line, only one parallel can be drawn to that line. And herein we have to a point exterior to a line, only no parallel can be withdrawn to that line, which is Riemann's elliptic geometry, or geometry on a sphere. And also Lobachevsky's, who was before Riemann, who developed the hyperbolic geometry, where through a point exterior to a line, it's possible to draw many parallels to that line. So in Neutrosophy, it's a generalization because it's referring to any geometric axiom, not only the fifth postulate in Euclid, and also to, for example, geometric theorems that neutrosophied, meaning transforming partially true and partially false. And anti-geometry means the geometry where at least an axiom is totally false. So the anti-geometry is a generalization of non-Euclidean geometry because it's referring to all kinds of axioms, while neutral geometry is an alternative and non-Euclidean geometry because it's referred to axiom that's partially true and partially false. So I have explained into this paper the distinction between neutral geometry anti-geometry, which is a generalization of non-Euclidean geometry, and other types of geometry. And anti-geometry and neutral geometry apply to all kinds of geometries. We have like Euclidean geometry, projective geometry, finite geometry, affine geometry, differential geometry, algebraic geometry, complex geometry, discrete geometry, computational geometry, molecular geometry, and so on. Then further on, some application of geometry to genetics was designed, and then was an extension to N super hypergraph. So the super hypergraph was defined as a general type of graph and extension of the classical hypergraph. And the definition is here in this website. So we consider, for example, introduce actually the super vertex, indeterminate vertex, null vertex, and in the same way, super edge, and so on. Now, Neutrosophic genetics here, it's in this paper. So how to use the Neutrosophy in order to create the mutation, use also the Neutrosophic theory and evolution, which is an extension of Darwin's theory of evolution, adding, beside the evolution degree, also the involution degree and the neutral degree, meaning the parts of the body or functionalities of the body that are not changed, or indeterminate degree parts of the bodies or functionalities that we're not sure if they changed or not. So we have, in the same way for mutations, we have positive mutations that produce a benefic effect in a sense of evolution, neutral mutations that produce no effect with respect to evolution or involution, and then the negative effect also. And speciation, it's given for the speciation also, we say TIF degree of speciation. So we have speciation when we have actually a Neutrosophic cut, when the degree of evolution, we consider it's greater than some value, and involution, indeterminacy and falsehood or involution, it's less. And then continuation is this T, it's indeterminacy, it's greater than some given threshold, and T and F are less than some given threshold. Besides evolution and Neutrosophic evolution, we have also introduced the super hyperalgebra and Neutrosophic super hyperalgebra, where we defined we define the super algebra on a power set of a power set of a power set, like in our everyday life. For example, if we have a set, let's say a given society, then this society is structured into groups um, or associations. Some elements may not be associated, doesn't matter. And then these associated associations also group into super associations, and then also even higher super associations. So that's why instead of considering only the power set of a set, we consider power set of a power set of a set, then power set of a power set of a power set of a set. So we said power set index n of a set to comprise all such connections. So let's see some examples here. For example, we may have a set of two elements CD, and then we combine them. C combined with C, we get, as you see, a set of two sets. And D also, it's a set of three elements. And this one, it's a set of three elements. So we get more and more complex. Okay, let's consider now the super hypergraph. In the same way, we have all kinds of connections, and this one is considered the most general form of graph. And we have, for all of them, the vertices. So the definition is the following: the vertices are grouped in sets of vertices, and then sets of sets, then of sets, and so on. So we have power sets as in our everyday life. So we have some individuals, then they're grouped into, let's say, some associations. Then some of these associations are grouped together, put together in other associations, and so on. So that's why we have power set of power set of power set of V of the set of vertices. And same thing for the edges. We have edges that are combined in groups of edges, then groups of edges, and so on. So we get a few categories of vertices: single vertex, vertexes in our everyday life, or indeterminate vertices, vertices which are not clear, vague, or partially unknown, null vertices, vertices that have existed but disappeared, had vanished with time. And same thing for supervertex. Supervertex is a connection, it's a single indeterminate or null vertices. And then we have also vertices of vertices, and so on. So this looks to be a classic, most general types of vertices. So as you see here, we have, for example, a set of vertices. We have from V1 to V6, 6 vertices, and we have edges that connect them. Now we have super vertex means SV means connection of vertex V1, V2, and V3. So we put them together and they form a super vertex. Now V1, V2, V3 also consider here separately, but if we put them together, we form a super vertex. Now we have, for example, vertices V7 and V8, and we don't know exactly what kind of edge is here, what kind of connection. So this is an indeterminate edge. Now, we may consider also multiple edges, for example, between V5 and V6. This is an edge, but we have also another edge. So we have multiple edges. Now, the red closed curve here forms a hyper edge because it connects the vertices V3, V5, V6, V3, V5, V6, and then also has hyper edge, and so on for the others. Similarly for the function was also extended. If we consider, let's say, a system formed by this is the first system, then the system is formed by subsystems, S1, S2, S3. So system 1 is considered a system, but the original is considered a level 1 or root. Now, S1, S2, S3, it's level 2. Then S1, the subsystem S1 is formed by subsystems S11, S1, 2, S1, 3. Similarly, the subsystem S2 is formed by subsystems S21, S22, which is level 3. And further on, we have level 4. We have subsystems S1 to 1, S2, S1 to 2. So in the same way as we're organized in our real life, we can write this way. This is the big system, the first one, which is formed by 3 subsystems, this one, and this one. Now, this one here is formed by 2 subsystems, and this one, S1, is formed also by S2, formed also by 1, 2, S1, 1, 2, 3 subsystems, and this one subsystem is formed by 2 subsystems, and so on, like in our everyday life, or we can write them in an algebraic representation. So you see the set is formed by 3, 6, 7, 8, 9 elements. Then we have here the subsystems A, B, C, D, 1, and then F, G, H, 2. So this is one subsystem. This is the second subsystem. And this is the third. And then again, each one, the first subsystem is split into subsystems and so on, up to here. Then subsystems. So the way how try to represent our everyday life. Now for super hyper function, we come back, super hyper function. So a function defined by a power set of S. So here it's a power set of S, but we may have even more power set of power set and so on of S. And this is the operation, and see how we combine the elements. So we may have a set of subsets combined, this one with this one, let's say combine with this one, and gives us For example, the same thing, A, it's actually the neutral. Here looks A to be the neutral element, but this one combined with this one is this one. So this is the way we define the super hyper function. And we also have super hyper function. And again, another example of super hyper function. And in the same way, we can define the super hyper topology and Neutrosophic super hyper topology, therefore, using instead of the power set of an element of a set, as in topology, we can use the power set of power set and so on, power set of index n of S together with some given operation. Then among the last ones, we have the new types of indeterminate soft-set and indeterminate hyper-soft-set. So indeterminate looking for indeterminate soft-set examples. So this is the soft-set indeterminate operation. Classic subset, indeterminate subset. So indeterminate subset is the soft set F defined for A with respect to P of H, but in such a way that we have some indeterminacy with respect to the function or the set of attributes or the power set of H. And such examples of hyper indeterminate subsets So example of indeterminate operators. So the operators are not clear. We are not sure how to find them. And we get indeterminacy. So the last thing is about applications of Neutrosophics. And this is a paper written by Xing Song Peng and Jingo Dai. And they present the applications from 1998 to 2017 and show the applications in artificial intelligence, information systems, computer science, cybernetics, theory, methods, mathematical, algebraic structures, and so on, mathematics, engineering, big data, operational research, mechanics, neuroscience, radiology, nuclear, medicine, interdisciplinary, and so on. We have also the Neutrosophic numbers that were used in order to deal with Neutrosophic algebraic structures and fuzzy cognitive maps and Neutrosophic cognitive maps together with Dr. Vasanta Kandasam from India. And then you can see connections, if we have positive or negative connections, but we can see also in the Neutrosophic way, if we have degrees. So -1 means negative connection between two elements, 0, no connection, and 1 positive connection. We have also cases where the connection is presented in the form of TIF, meaning 60% good connection, 20%, for example, wrong connection, and 30% indeterminate connection. There are also encyclopedia of Neutrosophic researchers. So we have hundreds of people. Actually, the last time we got like about 7,000 Neutrosophic researchers that published papers, presentations, or had PhD thesis on the Neutrosophic sites. Thank you very much.